Hello, welcome to Module 5, Week 1 of our course on Introduction to Dynamical Models in Biology. In last three modules rather, we have discussed how to make ordinary differential equation based mathematical model to understand dynamics in a biological problem. Remember, the key issue in case of ODE based model is that you write one or more than one ordinary differential equation representing rates of the processes involved, and then you integrate those ODEs to generate a function which gives you option to analyze the system and get answer to your questions. So for example, if you remember that the question of spread of infectious disease, when we were trying to model that one, we wrote a ODE representing the rate of change in fraction of population that is infected, that was dx dt was equal to r into 1 minus x into x. Now this is the ODE, ordinary differential equation. We integrated this ODE with initial conditions given to us and we got a function for x. So this x is a function of time. So by integration we got this one. Now if we replace the value of x0 in this function and the value of r with a numerical value, then we can know what will be the fraction of population infected at a particular time t. Or rather, if we take different values of t for a fixed value of x0 and r, then we can draw a graph like this one has been shown here. Now this we have discussed for 2-3 problems. For example, growth of population, logistic growth of population, like that. Now this procedure, this technique has one problem. Here what we are doing, we are integrating a ordinary differential equation using symbolic math. This method is called analytical method of solving the problem. Now the problem is, for many ordinary differential equation, particularly which are non-linear ordinary differential equation, it is usually very complicated to solve those equations using symbolic mathematics, or rather analytically, the way we do it, we have done it earlier. In many cases, the ODEs, number of ODEs in our problem will be very large. In those cases, it becomes very complicated to solve them again by symbolically. And particularly this is true when your system of ODE is actually coupled ODE. And that will happen very frequently in biological problem that we will deal with. So in all these cases, usually either it is very complicated or we do not know right now the method to solve these equations. So how do you approach this problem? If you do not know the method, or if the method is very complicated to solve, then how will you solve this system of ODEs? Thankfully, there is some numerical methods. Numerical methods are very useful because we can implement them through computers. So actually we can ask computers, even your desktop computer, to solve a particular set of ordinary differential equation and give us the answer. Now in this module, we will discuss about the general aspect, the basic features of this type of numerical solution systems, or rather algorithms for numerical solutions. Now before we go into that, let us look into some basic aspects of numerical methods. Now remember, the first issue is numerical methods are actually not exact method. They are approximate method. And the approximation is such that they are workable. So whenever you are using a numerical solution for your ordinary differential equation using a computer, you have to remember that the solution that you are getting is an approximate one, and we have to take care so that the approximation is as close as to the real solution. In this algorithm, we do not actually get a function of the way we have got in case of integration. By integrating analytically or symbolically, you have got a function for the dependent variable, but when you are doing numerical solution, you will not get a function. Rather, what you will do, you will get a data for changing the value, different values of the dependent variable with at different value of independent variable. For example, if we numerically solve the ODE for the spread of infectious model, we will have data for each time point, we will have data for x. So we get numerical data. Now that numerical data can be used in various ways. You can make a plot with time in the horizontal axis, whereas the x, the fraction of population which is infected, in the vertical axis. By doing so, you can visualize how x will change with time. And in fact, that's what you want. So numerical solutions actually give you direct data which may be approximate slightly, but it gives you a direct visualization you can have, so how the dependent variable is changing with independent variable. Thankfully, there are many algorithms for numerical solutions that are available. Some are very good for a particular type of systems, whereas the others are better for other types of ordinary differential equations. And in fact, most of these algorithms can be implemented by most of the common computing languages that you use, whether it is C, Fortran, or if you want to use MATLAB, you can actually write a few lines of code. These languages have library functions made by somebody else, which you can use for solving your ODE numerically. At the other side, actually, there are many plug-and-play softwares where you do not need any knowledge of programming. You can simply write down the equations for the ODE and ask it to solve. So numerical solutions for ordinary differential equations are very advantageous because we already have many ready-made tools for that. So let us look into the basic aspects of numerical solutions of ordinary differential equations. There are many algorithms, as I said earlier, for solving a system of ODE or a single ODE by numerically. I will start discussion with Eulers method because it is the simplest one to understand. Remember, Eulers method has a extensive mathematical background. I will not go into those exhaustive math. What I will try to convey to you the basic message of this Eulers method, the basic issues of this method intuitively. So let us start with the example. We have a differential equation here representing the rate of spread of the infectious disease, dx dt equal to r into 1 minus x into x. You have seen this equation earlier. Now I want to solve it numerically using Eulers method. So the first important thing that we have to understand. So dx dt is actually where change in x and time are infinitely very small, infinitesimally small. I can approximate it considering there is a finite change in time, that is delta t, and there is a finite change in x, delta x. So dx dt with approximation, obviously the very approximation, is equivalent to delta x by delta t. Now what is delta x? Delta x is value of x at time t plus delta t minus value of x at time t. So delta x is nothing but value of x at t plus delta t and minus x at time t. So delta x by delta t is x at t plus delta t minus x at time t divided by change in time delta t. So once we have this one, then we can rewrite this first equation, that ODE, in this form. So dx dt is equivalent to x at t plus delta t minus x at t divided by delta t. So that should be equal to r into 1 minus x into x. We are getting this one from this first equation, ODE. Now if I rearrange these terms so that I keep x at t plus delta t only on the left hand side and everything on the right hand side, then I get this one. X plus at t plus delta t is equal to x at time t plus r into 1 minus x into x. Remember, this is coming from the ODE into delta t. That means if I will show it graphically. This is time t, x is varying here. At suppose time t, x is here, and after time delta t, this is delta t, so this is nothing but t plus delta t. I will be somewhere here, and this value is x at time t, this is the x at time t, plus r into 1 minus x into delta t. Delta t is this distance, the change in time. We call it time step. So delta t is the time step. So remember, r into 1 minus x and x is coming from the differential equation that you have written. So what is happening here? You start with t at a particular time, then you increment time by a small delta t, and then you calculate what will be the value of x at that t plus delta t. Once you have calculated this one, you can take another time step of delta t and again can calculate what will be the value of x at that. So in this iterative way, you can keep on going calculating value of x as I change the value of t with delta t. Now let us try this numerically. We will take the same example of spread of infectious disease. So our ODE is as usual, the last one, dx dt is equal to r into 1 minus x into x. And the formulation from Euler's method that we have got is that x at time t plus delta t is equal to x at t into the function that is present in the ODE into delta t. If you remember, to solve we require initial condition. So x naught at t equal to 0 is 0.02, r is 0.5, and delta t, the steps of time that we will take, is 0.1. Okay. So now at time t, x is equal to 0.02. So x at next time point, that is 0 plus 0.1, will be equal to x at time 0 plus r is 0.5 into 1 minus x at 0 into x at 0 into delta t is 0.1. So if we put this one, x at 0 is 0.02 plus 0.5 is r into 1 minus 0.02 into 0.02 into 0.1. 0.1 is for delta t, the increment in time. I have already done the calculation and it comes to 0.02098. So I have made a table here. At time t equal to 0, your value of x is 0.02, and you get by this calculation the value of x at 0 plus 0.1 will be 0.02098. Now that is the value of x at 0 plus delta t. Now that means my clock has changed by 0.1. So we will calculate what will happen at that point. So now at 0.1 our value is 0.02098. This value is coming from this one. Now again, if I increment the time by 0.1, that is delta t, I have to calculate what will happen at x at 0.1 plus 0.1. So this is time, and this is delta t. So again I will use the same formula, this one we are getting for Euler's method. So I have to take the value of x at 0.1 plus r into 1 minus x at 0.1 into x at 0.1 into delta t. So I know x at 0.1 is 0.02098, 0.02098 plus r is 0.5 into 1 minus 0.02098 into 0.098 into 0.1 is delta t. This will be equal to, as I have calculated earlier, is 0.02207. That value is shown here. So if you see this table, I started with time t equal to 0. It is given that time t equal to 0, the value of x is 0.02. I calculate the value of r into 1 minus x into into delta t. This value is this one. So I increment x by this value and I get the value of x at 0 plus 0.1 time point as this one, 0.02098. So that means I write the same value again. That means that when time is 0.1, the value of x is 0.02098. Again I calculate this one, that is r into 1 minus x into delta t. I sum this value with the value of x and I get the value of x at 0.1 plus 0.1 time point, that is 0.2 time point as 0.022007. So I write the same value here. So at 0.02 I have the value of x 0.022007. In this way I can keep on calculating the value of x at different time point with the increment of 0.1. As you can see in the table, initially time is 0, then 0 plus 0.1 is 0.1, then plus 0.1 is 0.2, and then plus 0.1, 0.3. In this way, I have done up to time 20. And the value of x at time 20, which is obtained here at the 19.9 time step, is 99.7903. Now, I have these two data, t versus x. I can easily take them and make a plot and generate a graph showing change in x with respect to time. The interesting thing is that the Euler method is very easy, and for a 1 or 2 equations, ODEs, you can actually implement it using Microsoft Excel. So in here I will show you how I have implemented it in Microsoft Excel. I will strongly advise you to do it yourself using Microsoft Office tool that you have. You must have Microsoft Excel with you, and try this one. So what I will do, first I will put the header. First one is t, time. Next column is for x at a particular value of time. Then I calculate r into 1 minus x into x in the next column into delta t. There is an increment in time. You have to adjust the size of the cell. Then you have new value of x, updated value of x at time plus delta t. So let us fill the value. So this is the header. First time point is 0. At that time point, our value of x was 0.02. So now I use the formula of Excel to calculate what will be the value of r into 1 minus x into delta t. R is given as 0.5 into 1 minus this one. See how I am choosing C2 as a value for x into C2 into delta t is 0.1. So now this is my increment, that is 0.5 into 1 minus C2, because C2 is holding the value of x at that moment, into C2 into 0.1. In the next cell, we increment x by this d2. So C2 plus d2, that is the incremented value of x. That is the value of x at 0 plus delta t. So in this way, we have calculated the new value. So we increase the time. Time should be incremented by 0.1 step. So this is the value in the previous cell plus 0.1. So I get 0.1. Now the value of x for this will be coming from the E2 cell, because that is the value we calculated. So we will make that one equal to E2. So So that is the value of x that we calculated earlier. Now we have to calculate the increment. So I simply pull down, apply the same formula which is present in the D2 cell. So you note down that now it is 0.5 into 1 minus C3 into C3 into 0.1. Similarly, pull down and apply the formula present in E2 to E3. It is now C3 plus D3. So that is the value of x when my time point is 0.1 plus 0.1. So this way we have calculated the value of x incrementally. Now all the formulas are ready. I extend it and apply to all the cell till I reach time point 20. Okay, we have to do another cell. Okay. So we have got 20. At 20 time step, as you can see, the value of x is 0.9973. So we choose t and x column. These are the values we require, and I use the plot function to plot them. In the x-axis, I mark it as time. Y-axis is the value of x, so we mark it as x and finish it. We can remove this legend and the grid lines, adjust the scale because we require only about up to 20. Now I thicken the size of the line a bit so that it will become better. That's all. Now you have the behavior of x versus time as calculated using the ODE and solved by the Eulers method. And it looks almost similar to that what we have got earlier using the analytical method. Now let us look into the Eulers method in a graphical way. What we are doing here, look at this graph given here. Suppose at time t, we are at this xt point, This curve shown here is essentially function of x as a function of time t, and we have got it from a differential equation. We had a differential equation which was r into 1 minus x into x. From integrating that we got this function, and this is the function. At time t, we are at this point. So the value of x at time t is xt. Now we increment the clock by delta t. So our time point is this one, t plus delta t. And we want to know what is the value of x at that time point. So using the exact solution, the value will be this one, x at t plus delta t. But what we are doing in Eulers method is that at this point at time t, we are drawing a straight line having a slope which is equal to dx dt. And we are extending this line till we meet that t plus delta t position. So we get this value, this point. We take this point as the value of x at t plus delta t. So what we are doing, initially the value of x was this one, this is x at time t. We are incrementing this one by dx by dt into delta t. So this is the increment we have. So this is first part is actually nothing but slope, and the second part is the delta t, increment in time. But as you can notice, there is a gap between this calculated one and the real one. Now if I increase delta t, if I make delta t bigger, suppose I take this portion, this whole thing as delta t, a bigger delta t, then by my method I will have the value of new value of x here, whereas the real value is actually here. So you can see at every step what we are doing, as we are incrementing time by delta t and using the slope at a particular time point to get the new value of x through extrapolation, we are getting an error in our estimate. This is our error in estimate. This error in estimate can be reduced if we can make delta t smaller. Now let us see the effect of this one. See, it is the same ODE for the spread of infectious disease. The new initial value is same as it is earlier, 0.02. R is 0.5, and I have plotted different data. In your horizontal axis you have time t, and your vertical axis you have x. The gray line, as you can see here, the gray line is the exact solution obtained by symbolic mathematics or analytical method. We have done it earlier. I have done the numerical simulation using Eulers method, using delta t as 1 and delta t as 0.1. So one delta t is bigger than the other one. The black line shows when delta t is 0.1, my result from Eulers method. Whereas the dotted line shows the result from Eulers method when delta t is 0.1. As you can see, initially both analytical method and both the numerical methods are giving similar result. At the end also we have all these three matching together. But in between here and here, you can see there is a difference between different method. When delta t is 0.1, it is almost same as the analytical method. But when you are taking a bigger delta t, we are getting a erroneous result, and that is shown by this black line. So as I said in the previous case, that the correctness, the approximation, the goodness of approximation will depend upon what is the delta t we are taking. The smaller the delta t, the better result we will get, the error will be lesser. Now let us take another extreme example to understand this problem. In this case, the ODE is very simple. ODE is dx dt is equal to minus 10x. So it is almost like a exponential decay. If you do a integration with initial condition, you get this function x equal to x naught into e to the power minus 10 into t. X naught is the initial value of x when t equal to 0. So let us solve it considering x naught equal to 1. So look at the graph here. The black line is the exact analytical solution. I have not shown here, but if you take delta t for Eulers method to solving this system, delta t equal to 0.01, delta t equal to 0.01, you will get a solution which will be very, very close, almost exactly same as that analytical solution shown in the black line. If you take delta t slightly bigger, 0.05, which is shown in dotted line here, you can see for most of the part here and here, it is similar to the analytical method, but in some portion actually it is deviating and we have some error. But this deviation is absurdly very high when you take delta t equal to 0.2. Then you can see this bigger dashed line, the value of x is almost rhythmically varying with time, which is absolutely wrong. So what I want to show you here is that Eulers method is very simple numerical method which you can even implement in Microsoft Excel for a small system for 1 or 2 ordinary differential equation. But you have to keep in mind that this system is this algorithm is very sensitive to what is the step size or the increment size for time that you are taking, that is delta t. If you take very large delta t, then you will have erroneous result. If you take very small delta t, your result will be very good, but you have to remember your computation time will also increase. So to jot down the key points, what we have discussed in this video, in this module, is that analytical method or symbolic mathematical method that we have used to integrate a ordinary differential equation to get a function for our model is useful, but becomes difficult to be used when number of ordinary differential increases, or we have a system of ordinary differential equation, or you have a large number of nonlinear ordinary differential equation. In those cases, numerical methods, numerical algorithms for solving ordinary differential equations are very powerful too. Those numerical algorithms will give you approximate answers, but those answers are workable. We have to remember that in biological modeling, we will have large number of variables, so we will have large number of ordinary differential equation, and for most of the cases we will not be able to analytically or symbolically solve them, and we have to rely on these numerical algorithms. There are many numerical algorithms available. I have discussed the basic one, the Eulers method, to understand what is going on behind these numerical algorithms. We have seen that these are very easy to implement. Even in Microsoft Excel you can implement this one. We have observed that this method is sensitive to the step size or the increment in time that you take, that is delta t. If you take very large delta t, you will have error in your calculation. If you take small delta t, your computation time will increase. There are many other algorithms for numerical solution of ODE. We will discuss them in the next video, in the next module. Here we should keep in mind that numerical methods are very popular because in most of the languages, computational languages that are available with us, for example, starting from C to Fortran to higher level things like MATLAB, we already have library functions to implement this algorithm. At the same time, if you are not habituated with programming, there are some plug and play software, large number of them. You can use those to solve your ODE or system of ODE using a numerical method. So as a whole, numerical methods are very powerful tool and bread and butter in ordinary differential equation based modeling for biological system. Thank you for listening. See you in the next module.